All right, so today's lecture is going to be on life cycle assessment. This is very much out of my area of work, or even in general, computer science or electrical engineering doesn't deal with the concepts that are being dealt here. Uh, went through the slides of the previous lectures. You've been given some background on energy consumption. There was a lecture on batteries and what are the different things we care about. And this is gonna be a lot on the side of what is sustainability, how do we think about it, how do we go and optimize it and whatnot. We will connect it back to what we want to do with respect to E and CS towards the end of the lecture, but feel free to ask me questions about it in between. So in case you can call me Bharat. I'm a postdoc with Professor Srivastava, and I've been at UCLA for a year. Before that, I was a PhD student at UC San Diego, where much of my work was related to energy efficiency in buildings. So part of the thing that Mani wanted to bring in towards this course was expertise on how do we think about energy in buildings and save energy and whatnot. So I'll get started. Uh, why do we want to be energy efficient? First, we want to just spend less and do more. So in terms of just money that you are spending, that might be beneficial economically. And secondly, you might have energy budgets depending on what you're working on, especially if you're working on really low power devices, on battery, cell phones being a classic example, or even energy harvesting like indoor solar and whatnot. Uh, Secondly, the impact on climate and how it can lead to global warming, toxic materials that are released in the environment, fresh water being a limited resource, etc. So the classic example when we look into energy efficiency, even if I just type energy efficiency in Google Images, one of the first images that pops up is the light being replaced. Like the old incandescent lights are like 90% heat, 10% light, very inefficient. And if you replace them with CFL bulbs earlier and now LED lights, then you will be a lot more efficient and the life of the bulb is also longer. But if you look at the big picture of, let's say, if you're replacing lights for your home, the energy consumed by the light is actually a very small component of the big overall energy footprint that you would have, or you and your family will have in the home. And this is pretty much the theme of the lecture, where we are going to try and zoom out and see what is the big picture, how are different things related to each other, and what we should care about when we are trying to buy products, make design decisions. Lots of different phases where this would apply. So this, we do it in computer science and electrical engineering to a certain extent. And one of the popular things that we follow is Amdahl's law, where let's say you have like a process which consists of two parts, and even if you spend a lot of time on one part which consumes 30% of your time, let's say I want to run this as fast as possible, even if I make it 5x times, the overall speed depends on the first component, which still takes up 70% of your process time. So when you're trying to optimize a system, you want to look at what is the bottleneck that is causing the slowdown in your system, and then try to optimize. Even a small amount there is going to have a large impact in the overall process. So this is pretty commonly applied in computer architecture, operating systems, software optimization in general. Have you guys heard about Amdahl's law before? Show of hands. Okay. So what we are trying to do here is apply this on energy, on carbon dioxide impacts, on the toxicity levels that any service or product may bring about. And how do we do this analysis, and how do we then go ahead and optimize something that we want? So you take everything from scratch, where does the raw material comes from, how are these gets processed, how do they come together and make a product, and how do they get used in practice. So gasoline cars and whatnot, the amount of fuel that you burn throughout the life of a car is a big part of its carbon dioxide impact or energy impact. And end of life, typically how do you put it in? Do you put it in the landfill? Do you recycle it? Can you reuse it in some other way, etc.? And you're looking for impacts like global warming potential, how much water is being used, is something getting polluted. For example, depleting a freshwater resource of oxygen can kill a lot of the animals in a lake or in a pond, and those are very negative impacts that we want to stay away from. So these are all, any metric that would make sense for your analysis will be included in your analysis. So a lot of companies go ahead and do this for their products. This is the Ben & Jerry ice cream and their analysis of what are the different components. And in this case, they are doing carbon dioxide. So every tub of ice cream is 2 pounds of carbon dioxide, which is equivalent to driving 2 miles on an average car. And it's a revealing thing to do because they kind of figure out what are the different things that actually consumes most of their carbon dioxide and what do they need to optimize for. These companies spend billions of dollars trying to optimize each of their processes, both for cost but also for environmental impacts. And here we can see that ingredients actually are the major component of the ice cream tub that we're looking at. And these ingredients, the only power they have is perhaps sourcing from where it comes. But they have tried to optimize the things that they do, and they show that, okay, this is what it looks like on a big scale. So another example of jeans, Levi's jean pant, one of the standard models. So they have some amount of carbon dioxide emissions, 4,000 liters of water, which I was pretty surprised at, and some eutrophication impact, some land usage per jean. This gets interesting when you start breaking it down. It's like, where is the water usage coming from? So most of the water is actually, again, from the raw materials. The cotton that is used to generate the fiber takes up most of the water. And where do you source this cotton, whether it comes from India or whether it comes from China, all of those also start figuring into your equations on how much they will have impact on the final product. And consumer care has such a big component, mostly because of washing machines, that how frequently we use and rewash. Yeah.
So in this analysis, like in the cotton, do you also consider like when you grow cotton, it takes water?
Yes.
That is also considered.
That is also considered. That's why the fiber component is like that. And similarly, carbon dioxide emission, if you break it down, again, a big portion is the ingredients that is being used for generating, like fabricating the pant, and a very big portion is actually consumer care. And now this depends on the type of washing machine that you might be using. So depending on which country you're from, the average energy consumed by the washing machine is different. And there are different models of washing machines. Some are efficient, the more modern ones have Energy Star rating and whatnot, while some are not. So all of these considerations also come into play when you want to strategize for a certain region, for a certain type of product and whatnot. So to give you a formal definition as given by the international standardization body ISO, you essentially take into account all the inputs and outputs that are coming out of a product and assess what their individual environmental impacts are. Most of this analysis tends to be on the environmental side. Very rarely they look at cost or economic or social side of things. And there are different kinds of analysis which do that too. But much of the talk that we will have today is going to be about environmental impacts like carbon dioxide emissions or energy or toxicity and whatnot. And finally, once you compile all your results, you have to have a good way of interpreting what they mean. So what does it mean that my pants had 4,000 liters of water consumption? I don't have anything to compare it with. So much of the life cycle analysis or assessment happens on a comparative basis, and we'll come down to that again. So before that, a little bit of history. So this is LCA is typically attributed to Coca-Cola in 1969 or so when they wanted to figure out whether they wanted to do cans or bottles. I don't know where they what they ended up with. We have both of them today, so. Anyway, but at the complexity at which LCA deals with, and because there could be thousands of different components that you're looking at for your product, you can be malicious or do it in a way that is not that might be biased, and these can lead to results which actually turn out to be biased. And there have been several of them in you might have read in news articles like. A Hummer is more energy efficient than Toyota Prius if you actually take into manufacturing. But turns out there was a biased results. There have been quite a few of those. Like solar panels are actually more inefficient compared to gasoline, but now you have to do the analysis correctly, and solar panels are indeed better. So if these biased results drive the results of or your decision making, then it's not going to be effective anymore. So this happened a lot in 80s, and this was used for advertisements where people were told a bunch of results, but they actually didn't make sense because the analysis was not done in a fair manner. And this led to like a lot of lawsuits, and people had to stop doing it and whatnot. Then in the 90s, there were standardization bodies formed, and they figured out, okay, we need to have a more formal method of doing this, and everybody has to stick to this methodology, and then we can go ahead and do some comparisons. And that's where the ISO standard came up with. And this is what the standard says. And in almost every life cycle study that you will see that figure on the right, where you will have a goal that you want to study pants or ice cream or cars, and then what are we going to study about this? It could be a tub of ice cream. It could be like 10,000 tubs of ice creams. So you want to define those kinds of things at the beginning, and then figure out, okay, what are the different things that goes into this? What are the impacts of that? And then finally combine all the different impacts and figure out how much carbon dioxide they're emitting or energy they are consuming and whatnot. And throughout there's an interpretation process, and I'll come to that. So we're going to dive into each aspect of this with several examples, but this is the overall picture, and this was what was standardized by the ISO. So like I said earlier, people usually compare two things because it's very hard to see one product on its own and then actually make sense of what I make out of it. So this is a hand dryer study which was done at MIT, and they looked at what is the impact of using paper towels versus typical electric dryers versus Dyson, and much of the thing was focused towards what Dyson does because they had lots of information on how the Dyson product itself is made, and they wanted to promote the product and whatnot. So as you can see, paper towels, their use period has a big impact because we continuously use paper, and that leads to per drying hands, per use of the unit, you get a larger carbon dioxide impact. And this is the comparison is what gives you a good way to figure out, okay, this is what I want to use, this is the way we want to go with our decision making and whatnot. And another big part of how you do life cycle analysis is, in technical terms, is called attributional or consequential. So a lot of the earlier studies that I showed you, the ice cream and the pants, they were figuring out where does each portion of my manufacturing is contributing to the overall impact. But there's also consequential. Okay, what if I change my cotton produce from this country to that country? What happens? Will that actually reduce my total impact or not? And that is called consequential. Consequential, the kind of things you look at starts differing because you don't need to look at necessarily all the different things that you use in manufacturing, but it might be things that changed because you made this decision. So they go in like very different directions in terms of actually what you do. Much of the talk that I'm going to do today is about attributional, but consequential is the one which is probably going to help with a lot of decision making. Okay, so I'm going to go down to how to do LCA in general. Before that, any questions, any comments? All right. So the first thing that you need to do is define what is a functional unit. And this is essentially what is it that you are evaluating. And in case of the ice cream, it was pretty straightforward, one tub of ice cream. It doesn't need to be some standardized metric. In case of the dryer study, it was a pair of dry hands from wet to dry. How much impact is it going to have? And every study will have to take a hard look at what they want to analyze and then go about figuring out how these impact different things that they want to study. So this decision is actually going to impact much of the analysis, and it's a fundamental part of LCA. If you get this wrong, a lot of the later part of your analysis will be incorrect. Next, you have to figure out, okay, in the case of hand dryer, I want a pair of dry hands, and what are the different things I want to study about this? So you scope out, these are the number of different models of dryers that I want to look at. What are the different things I'm looking at with respect to these dryers? For paper towel machines, you want to include the paper towels themselves in the analysis. So defining the scope of the problem becomes an important part of where your analysis will lead next. So a lot of these LCA analysis also have these terms called cradle to grave. So cradle to grave is kind of like a complete analysis from the raw manufacturer, so raw materials to the point where you recycle it. But you can also have things like, okay, we get it to the point of shipping, and after that, we don't care how much impact it has, and that's called cradle to gate. Well to wheel is more on the okay, it got through the transport side, and then I don't care after that. So you could have different scopes in terms of the system level that you're covering also. So let's take the example of a biofuel, and we want to define its scope. And let's say it takes, okay, there's something that you farm, and then you transport it to the place which is going to generate the fuel, and then the process of generating the fuel itself. However, this we have to take into consideration what kind of things go into the processing, what kind of things go into the transportation, and these are called the secondary processes for your initial process. And this process is essentially can never stop. You can keep going on in this and like look at, okay, this raw material actually depends on a lot of other processing, and this can even be cycling. So essentially, it's an infinite process. So to do your analysis, you have to figure out, okay, what are the different things I want to look at. So there are a set of cutoff rules that people follow to make sure they have a bounded analysis. Despite the cutoff rules, it does take a lot of effort to get an LCA done for a normal product. So the first choice is incorporate everything, not going to work in practice. Second is incorporate everything that's at the secondary level or at the tertiary level. So you just define the level of analysis and then you just stop there. Third one, and this one was actually used in the hand dryer study, where you look at everything that goes into this and then have a ballpark estimate of how much they are going to cost in terms of impact, and then exclude everything that has less than 1% impact. But while doing this, they also made sure that the total things that they're removing will have less than 5% impact. So if it starts having more than 5% impact on water, then they start adding it back until the overall thing becomes greater than 95%. Other rules, you can you make a assessment of how these are going to have an impact on your carbon dioxide and then remove them. This can be pretty hard to do because you have to basically do the tracing to a large amount and then figure out how much you need to take out. And finally, you can exclude certain things like the hammer that I'm going to use for this process gets replaced every 6 months, but it gets used across a lot of different products. So I'm not going to include this category of things at all. So anything that's with capital equipment, I just assume they have zero carbon dioxide impact. So these define together the scope of what you want to study. And then you want to go ahead and actually figure out how these are going to have an impact. So the inventory analysis, it's also typically called life cycle inventory, and that's why LCI. Consists of two different things. First, so in case of the hand dryer study, you want to get what is called bill of materials. So people who have done some hardware, they might have heard of this term because you need to give this when you're manufacturing your PCB and whatnot. You essentially include each and every little thing that will be required to assemble this product together. And the activities is actually, okay, the material itself has some impact associated with it. So you want to include all of the different activities, not only the materials that go into your list, so that you take into consideration everything. And the scope is already defined in the previous stage, so you stop at wherever the boundary of your scope is. And secondly, there is unit processes that is required to put these things together, and each process will have its emissions. So you want to figure out what each unit process in your manufacturing is. And I'll give you an example, and it'll get a little bit more concrete on what exactly that is. And then you figure out what are the impacts, and then see what are the final impact that you will have on the environment. So this is what a unit process look like, and this could be things like, okay, I'm going to bottle the cap, put the cap on the bottle. This could be just one process, and you figure out how much electricity, gas, etc., that goes in, any transportation materials that are needed, etc., and what are its outputs that it might generate, any hazardous materials, any carbon dioxide, and whatnot. And finally, you get the finished components, which can be used further for the next process. So taking an example of an electric and gasoline car, you would have first its raw material, which would be things like electricity, and electricity itself needs electricity, coal, and gasoline, and then you go and figure out how the coal for that gets generated, and then the coal itself needs land and electricity and gasoline impacts of its own, and you put together all of these, and you can see that this can quickly get complicated. And this is a more realistic example of a solder that the US EPA studied. And this is like, you want to figure out if you have a lead solder that you use for your PCB soldering and stuff, how much impact will that have? And even that small material has lots of different things that you need to take into account and to make sure that the LCA actually makes sense. And this study was actually comparing lead solder and lead-free solder, and does it, just by labeling lead-free, does it actually make it more environmental, does it impact the environment as much as not? So once you once you have all of these different materials, you want to actually see, let's say I used 3 grams of copper, but you don't want to go out and figure out what the copper impact is and then actually figure out how much it's going to impact in each process. That's going to take indefinitely. So there are lots of tools and databases available which have this information for you. So it will say, like, if you have 10 grams of copper, it's going to have X grams of carbon dioxide impact. It's going to take this much toxicity, like phosphate, to manufacture this copper and whatnot. So there are tools like Umberto and OpenLCA, which allows you to compile all of this bill of activities and unit processes in one single software. And then there are databases which put in the material impacts of different raw materials that you use, and you can compile them together. So it makes your life a lot easier. But a lot of these software can be really expensive. So I looked at the OpenLCA one. There's a search engine kind of interface they have. And you just type in their raw materials, then they will say, you need 15,000 pounds to get started with your license and whatnot. So there are some open sources, but there are open source databases available, but they are not as extensive. So I think the NREL database has about 600 different processes versus the paid ones had like 5,000. So there is a big difference on the information that's available in the free ones. So do you guys want to actually see the search engine interface of the NREL? I can do a quick demo if you guys are interested. Yeah? Okay. Let's see. Oh, this resolution is horrible. Okay, let me just type in any favorites for raw materials that you want to try out. Silicon. Oh, that's a good one. Okay, there are many kinds of silicon. Let's just go with silicon, see if it comes up with something. They don't have anything here. It's actually useful. Let's try silica. Nope. Oh, there you go. Bauxite. This is the where the mine thing. Where do you mine the material? That place. So there's a big description on what it does, where is it sourced from, and whatnot. Then these are the different sources where the information comes from. Administrative. Okay, so the exchanges is where it gets actually interesting, where we can see, okay, if you get 1 kg of the product, then it's going to have 7 kilograms of, no, 7 raised to e, like e raised to minus 4, so of carbon dioxide and all the different materials, methane, nitrogen, sulfur oxides, and these are the different things that you actually use during the mining process itself. So it gives a very detailed input, and then you take this into your tool, or a lot of times people end up using Microsoft Excel or something like that. So you put it there and then figure out how this is going to compute together. Okay, so any questions? You want to try something else? Okay. All right. So yeah, the slides are made available to you guys, right? So you can take a look at all the different URLs later if you want. Okay. So typically these data sources, given that you have an extensive list that you're looking at, we already saw that out of the 2 or 3 things we looked at, 2 of them didn't have any results. So this is going to happen often, where you don't get information for some of the things that you're looking for. So people look at other studies and papers and LCA reports that are out there and see what they have done. Look at other, like call up an expert in LCA and see what they have to say, or actually pay for the tools and databases and whatnot. So obviously you want to get as specific as possible if you want your analysis to be accurate. So there is something, this data sourcing has a huge impact on what the final result will be. So there is something called as uncertainty analysis that will actually bring this back a little bit, and you get to see if your sources were incorrect, then how much would it impact my final results. Okay, so next is impact analysis. So impact analysis is fairly simple. You just have all the different materials. It's a basic addition of different things that each thing contributes to. So just classify where, well, like this is carbon dioxide, this is the toxic material that I'm interested in, and then just add them up together. And you get charts like this one, or the ones that I showed you earlier with Levi spans and whatnot. So the hairdryer study, here they're looking at, excuse me, carbon dioxide impact, and their blades are very efficient, and even electric air blades, electric hair dryers like accelerator are actually very good because they use these high-speed motors. But paper towels during use, manufacturing of the paper towel itself, all of that add up to a lot of carbon dioxide, and thus you get this table. And this was the table that you get out of after you add up the impact assessment in the previous stage. Okay. But this final result can look and very different for different kinds of assessments that you do. So this is a study, perhaps one of the readings that you will do between EVs and gasoline cars. Were you guys given this paper to read before this class? Did you have any readings at all for life cycle assessment? No. Okay. All right. So this is one of the paper in the readings. I don't know how exactly the reading schedule is done. So, but if you have EVs in places where the electricity generation is more on the renewable side, the impact of having that EV is very good. Like the impact on carbon dioxide emissions and energy consumption is going to be very good. But if you go and actually do it in places where the amount of most of the electricity comes from coal or natural gas, then it's going to have the EV is not going to be as useful. It's almost equivalent to a gasoline car. So the place where the information comes in, and we saw this with even the washing machines earlier, that will have an impact on how useful these end products are in the different places. So that was a different impact analysis, and you can break down the data and look at different charts and figure out what they look like. But the final part is interpretation. What does this mean for us? And that is done using sensitivity analysis, uncertainty analysis, and bill of activity uncertainty analysis. And this is what I meant by the data sources being an important part. If one of the data sources you were not really sure of whether it's 10 grams or 100 grams, then how does it actually impact your final results? So to give you a concrete example, this is a different paper which again studies about the impact between electric vehicles and gasoline cars, and how would their use actually impact, or the different technology that goes into these cars actually impact the carbon dioxide emission of the whole life cycle. And the vertical line is the typical gasoline car, and everything on the left is efficient versus everything on the right is not. And you can see that, well, the diesel cars, which are the third category, is already efficient because they get around 50 miles per gallon by default. And the EVs are efficient, but if you have a bad electricity source, or if the batteries are not managed efficiently, then they start crossing that vertical line, and their impact is actually worse than the gasoline cars. And in the same way, if gasoline cars start becoming more efficient magically, I don't know how, then they would be actually a better option than using EVs, because electricity use in places comes from things like coal or natural gas, and that's not good for the environment. So this sensitivity analysis is you take into consideration each and every metric that you care about and start varying it, and then look at its impact. Sometimes you do combinations of make a scenario analysis. Okay, in this place, these are the different things that might vary versus in New York versus California, for example. And in California, these are the different things that vary, and then you figure out where the impact might be different. So that's how you use uncertainty analysis and interpret the results that you're getting, how robust it is to changes in minor perturbations in the raw data. Okay, so that's pretty much everything about lifecycle analysis, which I covered a lot faster than I thought. Any questions before we move on? No? Not that interesting. Anyway, so what we saw was cradle to grave, where it goes to raw materials and then goes up to recycling. There's a field called industrial ecology, which studies this sort of things, and they promote what is called cradle to cradle design. So most of their inspiration comes from biology, where everything in bio is a cycle which repeats itself. And in industry, we tend to have this philosophy of use it and throw it away. And if we do a little bit of recycling, reuse, then the throwing away part reduces. But if we have a cycle of completely taking whatever waste product we generate and reuse it in our manufacturing or daily usage, then you don't have this waste going on, and we are sustainable forever. So this is called cradle to cradle design. I talked to one of the experts in this area, and he told me it never really happens in practice, but it's a good way to think about. There's one factory in Netherlands, I forget its name, which actually has done this, where all of its processing happens in one place, in one complex, and they've managed to do this, but it just doesn't happen in practice because of all the practical difficulties you have. So that's one concept. Different concept is you want, after your product is, like, let's say, damaged or its life is done, you want to make sure that it can be reused for something else. And this is called design for disassembly. And this is used a lot in industrial design and figuring out what are the different aspects I need to change to make sure that I can disassemble the different components that exist to put it in a new product, or in the same product for a new version. So concepts, this is a design company called Lunar, which gives out these concepts for making it easy to disassemble, things like making it modular, make sure that there are good directions given to even a third-party repair person to take it apart and use it for different things. Use of materials obviously matters. You don't want to you want to reuse things which are not renewable, and use renewable when you can. The last point was here was that it's odd that when you use a lot of paint on these materials, it becomes hard to recycle them, because if the material has paint on them, it's hard to separate the paint out. So people end up throwing that material away. So if you don't have paint on your material, then it's just easier to use. Okay. So as an example, Toyota Prius has 85% recyclability, and 95% of all its material that goes into the car is recoverable. And they do go through, can you actually see this? Go through a lot of pain to actually make this happen, where the car, when it goes to the junkyard, each and every part is taken apart, reused, processed, and goes into either different industries which might have its use, or recycle into the car itself. So that was pretty much everything in life cycle assessment, to the extent I know. There's a whole course on life cycle assessment taught in both at UCLA and outside, but there are lots of related analysis that goes in, such as this listed here, and they all can be attributed to sustainability or cost effectiveness. So in buildings, people care a lot about return on investment. So if I install this huge solar panel on the top of my house, how long will it take for me to recuperate the costs of installation? So lots of different kinds of analysis which are similar in vein to life cycle assessment is done in industry, and they have these fancy terms. Okay, so finally, where does this all come down to in terms of computer science and EE? Why does it matter? All of this was like industrial processes and recycling, and we don't end up doing much of the work. So mostly because every little thing that you do has an impact. The software that you might be writing, or the next Internet of Things product that you make, will have all its impacts on the environment. Different things, different decisions will have different impacts and whatnot. So just to give you an example, the electric kettle is very popular in the United Kingdom. About 97% of the people have it, and 65% of them admitted in a study that they actually fill the kettle to its capacity, heat it up, and then they end up using it for only 1 cup of tea. And the rest of the water cools down again, and it's actually the energy spent for that is not getting used. If you take up the extra energy that is spent to heat up that water for one day across everything, all the kettles in the United Kingdom, it's enough to power all the street lights in the United Kingdom at night. So when you look at the kettle and give this problem to the designer, make this energy efficient, people don't look at its big impact. They look at, okay, maybe I should change its material from aluminum to something else, or they look at how do I make its heating more efficient. But the impacts of its function and how it's used is also a big factor in its carbon impact. Another interesting thing that comes with electric kettles again is, so a lot of these people have tea during when they're watching TV and whatnot. So when there's popular shows in that are playing, like let's say FIFA World Cup, then at the break time, a lot of people use the refrigerators and electric kettles at the same time, and this causes a spike in the electric grid, and the spike is really hard for the electric grid to handle, so they have to borrow energy from France, which has to compensate for the energy spike that happens during this break. And these are called TV pickups. During 1990 World Cup, the pickup was close to like 2 gigawatts, and typically it's like 200 to 400 megawatts, are up to, and can go up to 800 megawatts for popular things on TV. So again, your electric kettle, the one kettle that you had at scale, will have impacts that can be huge. So when you borrow these electricities from different countries or use extra capacity, these are all very energy wasting way of generating electricity. They are not optimized in the sense that you're how your normal electricity is generated. And that's why these have huge impacts. So somebody looked at this TED talk which showed all of these different things, and they actually decided to make a product out of it. So this is like induction heating, where you have a single handle, you put it in your glass, it will heat it up, and they cite the TED talk itself back that it actually wastes a lot of energy if you use the kettle. So use our product, which will just heat up your cup of tea, and you can then be energy efficient, and also it looks pretty and whatnot. Okay. Finally, where does all these computers and smartphones and different things that we use go? So there's lots of units purchased, and I think the last year or so was when the number of units sold was larger, number of units in use was larger than the population of the world. But a very few of them gets recycled. In case of smartphones or mobile devices in general, only 11% gets recycled. And these are the ones which are changing very quickly. Like every 18 months, 2 years, people change out their phones, and this generates a lot of waste. So in the United States, that's like 150,000 computers, 400,000 cell phones. And why does this matter? Like, what if it is wasted? If you were to take 1 million cell phones, you can actually get back a lot of the precious materials that are used in there. In fact, to get gold out of 1 kilogram of e-waste is more efficient than getting it from the gold mine and going and digging and taking it, doing the whole process of taking it out. So this is done in the industry now, where people set up whole recycle factories and take them apart and extract the gold and reuse them for different purposes. So every material is similar. So aluminium is a big waste. If you go from raw materials instead, if you recycle, you end up actually saving much of the energy that goes. So 11% goes to this, but the rest 89 go to a dump. And the people at the dump, they actually see the gold coming from that wastage is actually cheaper than the gold coming from the ore. So they actually burn these materials with all their toxic materials that's inside them to get the copper in this case, or even gold, and then ship it to different companies. And these companies can be back in the United States too. So this goes through a whole cycle. Okay. So a lot of different companies are making an effort to not let this happen. And how do you improve this whole life cycle process of being more sustainable? So Greenpeace releases its Clicking Green report every few years. I think this was 2015, where it rated Apple as the greenest, closely followed by Google and Facebook. Companies like Amazon are quite down the line. And so you can go to Apple's website and they list everything that they do about environment, such as their data centers are 100% renewable. I think Google is going to be 100% renewable by this year. Similar efforts are being made by different companies. So even materials like paper that they use in their offices, the toxic materials that goes into Apple Watch has been like devoid of mercury, beryllium, and whatnot. And finally, there is a special process, especially in case of iPhones. There's been a lot of advertisements where you've seen that they have built robots to disassemble your iPhones and reuse it in their products and whatnot. So I think Google's expenditure was around $2.5 billion just on their sustainability efforts, and Apple doesn't disclose that, I think. So this is pretty much the last slide, I think. What are the different things that we can do to make this better? So before I say things on the slide, when you look at things like smartphones and having their impacts, a lot of their impacts are actually just take into consideration what the charging takes and what the network takes. For example, like what does it take to have the access point live, keep it awake and keep communicating with the phone. But the phone is a network device, so it has impacts which are indirect. So when you're using the data center, the impact of the data center should be attributed back to the phone. A lot of these analysis becomes really difficult for these multifunction devices, as they are called. And also it's difficult because earlier we used to have a separate phone, a calculator, an email, and everything, and they're all combined together in one object now, and comparing that with the legacy devices is also very difficult. For buildings, this becomes way too complicated because normally when you do life cycle analysis, they only take into consideration the different material that goes into the construction and the electricity bills that the building has. But its use in everyday life is rarely taken into account. They do take into consideration different types of buildings like restaurants versus university buildings and whatnot, but even within university buildings, the energy variance is like huge, and this does not get taken into account. And finally, there's lots of opportunities here. So if you're interested in LCA and if you like this process of you want to do rigorous things for different objects that are in your life or different products you might be designing, then you could this process will help you do that. And even LCA itself as a field is struggling because of the lack of data sources. How do you combine them and whatnot? You can build products which actually make this a lot easier. Finally, there's all of these were actual objects. A lot of our lives goes into the world of software. What would be an impact of a software program if you take into consideration the effort that people put in to build a software product together and maintain it? There's a lot of energy that goes into it, and what would that be? So with that, this is the professor at UCLA who's at the Institute of Environmental and Sustainability, and he is an expert on LCA. I talked with him before I came here, and he would be happy to talk to you guys if you guys are interested. He's also looking for students for research, and he's going to take the whole course on LCA, I think, next quarter. So you can contact him if you're interested. All right, these are different references that I used, and that's it.